Hello everybody and welcome back to Calculosity. It's your host Corey, and today we're going to be talking about using limit theorems. So previously we talked about calculating limits algebraically, graphically, using tables, and now what we're going to do is we're going to figure out how to calculate limits of composite functions, that is, functions that are comprised of several other functions. So that being said, let's kind of jump into things and see if we can learn some different theorems today. Alrighty. So, just zoom in here. First and foremost, let's think of some functions to work with. So, I'm going to create a couple functions here. We'll create a function f of x, and we'll make it something simple, like x plus 2. Alright, and then I'm going to create another function, we'll call it g of x. Alright, and we're going to call that, whatever we want to. Yet again, choose something simple. We'll call it x squared. Alrighty, so now we need to think of a couple ways that we could combine these functions and figure out limits. But first and foremost, let's think about some basic limits of these functions. So let's find the limits of these functions, like f of x, and we'll find the limit of g of x as well when x approaches something that we can control. X approaches, let's say 2. I'm just picking a number. And so if we have the limit of f of x when x approaches 2, we're going to see that's going to be f of 2, because there's normal behavior of this function. There's no reason that x plus 2 is going to have any issues. There's no division by 0, no square roots of negatives, etc., etc. So f of 2 is just going to be 4. There's perfectly good behavior there. It's not 1 over anything. It's not, rather, 0, division by 0 or anything like that. So that's normal. We could also look at the limit of g of x as x approaches 2. And we're going to see that that is going to also be pretty normal. It's going to be 2 squared, which is conveniently enough 4. So we're looking at 4 for both. Now we need to figure out what happens if we combine these functions with addition, with subtraction, with division, with multiplication. What if we do a composition of functions? And let's tackle all of those questions. So here's the first theorem that we're going to deal with. We're going to work with addition. What happens when we add limits? And so this is our first question here. We're going to find that the theorem for addition is that the limit as x approaches a, just a general value, could be infinity, negative infinity, an integer, floating point number, it doesn't matter. So as the limit of x approaches a of f of a plus f, or not f of a, sorry, f of x. We all make mistakes, forgive me. Of f of x plus f of g. Falling apart, g of x. Okay, so if we do the limit of f of x plus g of x as x approaches a, we're going to see that the theorem here is that we can actually pull the limit into each of the individual terms, kind of like distribution. And we'll see that that's going to be equivalent to the limit of f of x as x approaches a plus the limit of g of x as x approaches a. Alright, so that's a fairly intuitive theorem in that, yeah, we should expect them to add up. They're just numbers after all. Each individual limit is just going to be a number. And remember, we're plugging in any well-behaved function. We're just really plugging in the value. So there's no reason that when we do the calculation of the left side here, if everything's nice and well-behaved, which is always the case with these limits, that if they exist, then they're going to be nice and well behaved, we can plug straight in and say that this is actually going to turn out to be f of a plus g of a. And that's going to be the exact same case here with this right side, is that we're going to end up plugging in into the individual pieces and it's still going to become f of a plus g of a. So that's how they turn out to be exactly the same. This works out really, really nicely. So here we can actually use the addition here. We can set our a value to be that value we calculated earlier, which is 2. And we can actually do some of these calculations. So we can do f of x plus g of x as x approaches 2. And we'll see that it's going to break into the two pieces, the two individual pieces, the limit as x approaches 2 of the right, of the f of x, and of the g of x. Just a lot of writing here with all this notation, so bear with me. Alright, and we're going to see by this that we're able to break it up, and we know the answers for these already. We know that the limit of f of x as x approaches 2 is 4, and the limit of g of x as x approaches 2 is also 4. So we can go ahead and just substitute him in, and we just get 4 plus 4, which is equal to 8. Works out really nicely. And in fact, we could have done it the other way too, because it is really just substitution. We didn't have to break them apart if we didn't want to. We'd just be substituting the 2 into f of x plus g of x instead of subbing the 2 into f of x and then adding the g of x. So this is the important theorem for everyone to remember. That is this guy right here, that you can break up the limits into their pieces and calculate them that way. And so we're going to see a pretty common thread across all of these different limit theorems, is that we really can break them up at every stage of the process. So now let's look into what if we want to subtract, and it's going to be the exact same thing. In fact, we probably don't even have to really look through it, because subtraction is really just adding the negative, and that works exactly the same way. So let's jump over subtraction and get really right into multiplication. Alright. So 2, we're going to deal with what happens if we multiply two different functions together and then take their limit. So multiplication. And this theorem is going to look really similar to everything else we've already dealt with. And that's going to be that if we're multiplying into a function, so we're taking a limit as x approaches a of a function f of a, or f of x times, this is a time symbol, not a composition, times g of x, then we're going to see it breaks really nicely into two pieces as well, because yet again, we're really just plugging into these functions, so there's nothing super special going on here. Other than that, we're plugging into them individually instead of plugging into them at the end, after the multiplication. So this is as x approaches a, and that's nothing super special. Yet again, just like before, we can figure out what happens as x approaches 2. My handwriting will get a little bit sloppier so that I can get this written quickly. But as x approaches 2, we'll see that it break apart like that before, and we can just multiply the individual limits, which is yet again going to give us a nice happy 4. Alright. Now, what has got a little bit of a different clause added to it is if we want to deal with division, because division is exceptional because we have to worry about dividing by 0. So what comes out here then is that division, let's just write down division. So when we're dealing with division, we have to be concerned about division by 0. But other than that, there's not a whole lot of limitations. So let's look at that. As we do the limit as x approaches a of a given function divided by a given function. So say f of x divided by g of x. Mind you, we could substitute any f of x and any g of x into these. These are all general. That's why we're using a in just general function signatures instead of using the actual values like x squared, x divided by 2, etc., etc. So we have the limit as x approaches a of f of x divided by g of x. Well, that is going to be exactly equivalent to the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. The only stipulation is that the limit of g of x as x approaches a, this cannot be equal to 0, because if it is, we have to worry about division by 0. Because remember, the function value will not always be equivalent to the limit value. And, if you want to see an example of when the function is not always equivalent to the limit, remember those removable discontinuities from earlier. What if we had a function that had a removable discontinuity? Mind you, we're going to talk about removable discontinuities when we get into the actual continuity section. But we could have a function that has a removable discontinuity, but has a point above it. So this means that, say f of 2, that could be equal to 4. But the limit as x approaches 2 of f of x, this might be equal to 8. Or sorry, not 8. Sorry, this is actually lower. Equal to 2. Remember, the limit is where the line appears to be going. So in this case, it appears to be going to that little dot right there. Or to the hole, rather. But the actual function value is the point that exists at that x value. So that's the distinction there. So here, since our limit does not equal our function value, it's very possible that we can plug it in to the limit of x approaches a of f of x over g of x, because we can, in fact, plug a into g of x. But perhaps we won't be able to plug a as the limit perhaps the limit of f of g of x as x approaches a, that could turn out to be 0, even though g of a is not. That would just require that we had some sort of removable discontinuity case where the limit is 0. But the original's not, because of this hovering point above situation that we have here on the right side. So you just got to be really, really vigilant and make sure that that limit of g of x as x approaches a is not equal to 0. Otherwise, we'll get division by 0, and they're not equivalent. But generally, if there's not a situation like that, we're going to be fine and dandy, as long as that limit does not exist, which could happen. Alrighty. So we've covered multiplication, we've covered division, and we've covered addition and subtraction. So now we just have to worry about what happens if we're dealing with composite functions. Composite functions being functions with functions inside of them. They're nested functions, that's what makes them composite functions. So let's look at some compositions of functions. So a composite function is typically notated as such, if you're familiar with the notation. Let me scroll down a little here, my bad. So f of g of x. This is equivalent to saying f of g of x. That means that we're nesting g of x inside f of x. This would look like, well, remember our f of x from earlier, since we can't see it anymore. I don't even recall, it was x plus 2, right? And our g of x is x squared. So since that's x plus 2, and our g of x is x squared. Now this is an algebra thing, so I'm not really going to be too concerned about covering how compositions of functions work. If you're not super comfortable in that, there will probably be a video in the future on how compositions work. But for here, we're going to take for granted the fact that we've made it beyond algebra. That's a requirement to actually get into calculus, so we should be somewhat comfortable with it. And so composition f of g of x of these two functions should turn out to be plugging g of x into f of x, which would say x squared is getting substituted in for x, and we would get x squared plus 2. That would be the composition of these two functions, f of g of x. So how does that affect our output? Well, there's a nice little formula, and it's very intuitive. So this theorem here is the composition limit theorem, and it is as such. So if we want to consider the limit of f of g of x as x approaches some value a, it's going to be equivalent to f of the limit of g of x as x approaches a. These are going to be equivalent because, yet again, we're really just substituting values in. So on this first one up here, it's going to give you f of g of a. And on the second one, we're going to substitute it in directly with the g, instead of kind of trickling down. So here we're going to still have f of g of a. It makes absolutely no distinction. They are still equivalent to one another, provided everything works out really fine and dandy. But if there's going to be a problem in the second one, there's already going to be a problem in the first one, because it's kind of hard to alleviate this whole division by 0 thing. I mean, granted, there are certain exceptions when there's cancellation, so we do have to be worried that the limit of g of a is going to exist, because if it does not, then we could encounter an issue. So this is barring any situation when this, let me circle it, when this is not equal to t and e, but the other one is, or rather, sorry, when this is equal to d and e, but the other one is not. So this cannot be equal to d and e. That's what I was getting at. Alright, so let's look at an example of it. So we already said the composition of these two functions is going to be x squared plus 2. That's the composition f of g of x. So let's see here. In the initial example, limit as x approaches a of f of g of x. We're going to use our normal substitution method. This is going to give us f of g of a, which is going to give us, well, first we have to think about our composite function. That's x squared plus 2, such that our x is equal to a. So that's what that bar means. It means such that our x is equal to a, so we're going to end up with a squared plus 2. Or if we want to use an actual number, like we've been doing, like we used 2, that would be 2 squared plus 2. So if we make this a equal to 2, then that would be equal to 2 squared plus 2, which is 4 plus 2, which is 6. Now let's look at it if we use the theorem. If we use the theorem, this is going to become f of the limit of g of x as x approaches a, which is going to be, we can calculate the limit of g of x on our own if we'd like. I should be using 2, I suppose, since we're using 2. So we already know that the limit of g of x as x approaches 2, we calculated that earlier, it's going to be 4. So this turns out to be f of 4. And what is f of 4? Well, remember what f is. F is x plus 2. So that means that this is going to turn out to be 4 plus 2, which is 6. So these are just some examples of this working, but I do promise you it's proven. We could have a situation in which, however, that limit of g of x as x approaches a does not exist. That'd be the case where our g of x is something like 1 over x, but our f of x is something like... well, that's pretty tough, getting something that would actually cause cancellation. We might actually be dealing with a situation in which we don't have to worry about that. So, maybe we should scratch that in its entirety, because we really don't have to worry much about that. I guess with I could still think of an exception, however. That would be if f of x was also 1 over x. That could give us an issue, because the composition f of g of x is going to be 1 over x. That would give us x. So in that situation, it would be completely safe to do the composition and then plug in if we were looking with as x approaches 0. Perhaps I should write it out for you guys. Oh no, I've been cutting it off the whole time. Forgive me. If our f of x is 1 over x and our g of x is 1 over x, the composition f of g of x, that's going to be equal to x. Now, if we were to do the limits of these as x approaches 0, we'd see that as x approaches 0 of f of x and g of x, they're going to be d and e. But if we do the composition first, the limit as x approaches 0 of x, that's going to be 0. So we see there that there is a discrepancy there if the limit of g of x as x approaches a is d and e, but not the original composition in its entirety. So that's something to be looking out for, so just be careful. But if there isn't any weird behavior, it will work out perfectly. But really, that being said, we don't have to worry too much about other stuff. There is always the question of what happens when there are constants involved, but remember, constants, well, when we deal with limits, we deal strictly with the variables. So if we had a limit that involved the constant really is completely ineffectual. It's not going to do anything for us. So, for example, we can just look at the situation where we have the limit. Let me write that out. So there's the situation in which we have the limit of f of x times c, something like that, where c is a constant, maybe like 3, maybe like 8. We could have that as x approaches some value a. But mind you, we'll put it in parentheses just in case, just so you can see the association. And so in this situation, we can actually just pull that c directly outside. That's nothing that we have to worry about. And we can do this in any case whatsoever. We can always pull those constants out, provided they're being multiplied in. They have to be multiplied in. If it's addition, it's not going to work the same. But keep in mind that those constants are not going to be affected by limits in any case, because the limits are only concerned with x's. So we can pull them out like that. If we have a limit with addition, something like this, f of x plus c, well, we can't exactly pull it out here. But what we can do, thanks to that limit theorem we dealt with earlier, where the sum can be broken apart, we can actually look at this with the addition theorem and say that this is actually the limit of f of x as x approaches a plus the limit of c as x approaches a. But mind you, there isn't a single a in this term at all. There's no a's in this term. So it's not going to be affected whatsoever. And so you're going to see that by rule, the limit of a constant, and this is, I suppose, an important one as well for those of you that hadn't already picked up on this, the limit of a constant as x approaches anything is equal to that constant. Big important rule. Goes without saying, but if it doesn't change at all, then no matter what x value you plug in, it's always going to output the same value, whether it be 4 or 8 or whatever. And so that makes this pretty straightforward. This is actually going to break apart with the addition rule, and it's just going to become the limit of f of x plus c. This kind of plays off the addition rule, but it's just important to note, at least somewhere, that anytime we're dealing with constants, the constants, they aren't very relevant. They don't have much effect on our output because they're not variables. But that being said, I think we've covered about all the rules, what happens when there's constants, addition, division, composition, multiplication of any of these functions, of any two or more functions. This could be extended outward to include more than two functions as well. But now that we know how the limits work generally and how we can break them up and simplify, we can work with some more complicated limits, and we can get them into their building blocks and better understand how to solve them. But that should do it for this lesson. I appreciate you guys all hanging around and listening in. Hope you've learned something, and I'll catch you next time for the next lesson.